Welcome back to the last day of our course. Let's start the day with Professor Pfeiffer's lecture on hyperbolic equations, using how to solve them using spectral methods. And today he'll focus more on problems without periodic boundary conditions, I guess.
Yes, boundaries at last. Good morning, everybody. Let me start, as always, with a very small return to yesterday. So this is where we stopped yesterday. We were evolving scalar wave equations in a Fourier domain. So this particular pulse is happily going right. It leaves on the right-hand side and then comes back on the left-hand side at time 3 approximately. And the one thing I wanted to highlight here, which I didn't do yesterday, which was part of your problem set, is I explained to you that the initial conditions for pi basically determine the precise split into left-moving and right-moving mode of your initial profile. And what I wanted to do now as a little last reminder of all of this is actually setting pi to 0. So I'm only starting with initial conditions for g and a 0 time derivative of g. And then, if I'm doing this step by step, what's happening is that my initial pulse is splitting in two in an equal combination of left moving and right moving, because that happens to be the combination that makes the first time derivative vanish. So after a little while, you have the pulse like that. If you go one cycle further, well, then these are going to move further to the left and right. You get the green curve. And if I go a few more output times, woohoo, these are perhaps one too many. Well, actually not, this is perfect. If you go a little bit more output times, you see the pulse splitting in two, becoming wider and wider, and ultimately realigning the two copies again at the boundary, giving the red curve here with another peak maximum. Then the one half keeps on moving left and comes in on this side. The other half keeps on moving right towards the middle. That gives us the purple ones, and then the brown ones, and then everything recombines in the middle again. So it's a flopping around, just a very special superposition of something going left and something going right. But, as I said, today is our goal to get rid of the boundaries. And so instead of having something that goes to the right and then comes back on the other side, like here, going to the right and then just wrapping around, we now want to do this with a Chebyshev domain where we want the pulse to either just leave and be gone, and or, at our discretion, we want to be able to feed in whatever boundary data we like, perhaps nothing at all, perhaps a new pulse, and we will have to do so on both sides. So we can feed in stuff over here, we can feed in stuff over here. Anything that travels left has to leave here without being reflected. Anything that travels right has to get out on the right-hand side. So that's the plan. And to do so, hyperbolic, or let's the wave equation in with boundaries. And to do so, the key thing we need are characteristic modes. So both I and Geoffrey have already alluded to this earlier. So let's do this in more detail today. So I have again our usual first order form of the non-conservative set of evolution equations, B alpha beta k, dk of u alpha u beta equals some source. And as Geoffrey, I'm also doing some convention. So here's a sum over the beta indices, making this matrix, allowing through this matrix to put derivatives of any of our variables into any of the evolution equations. And there's also, of course, the sum over k. So characteristic modes probe the high frequency behavior of this set of equations, and they split everything into nice traveling waves. So to get there, what we want to do is we want to probe precisely the short frequency limit of this set of equations here with plane waves. So we are starting out with assuming that our solution is some constant times, well, a traveling wave, e to the I kx minus omega t. And this is just the set of amplitudes, how much contributions you have in each mode that is happily traveling along here. The k here is a combination of the wave number, that is 2 pi over lambda, the period of the wave, and the propagation direction n hat. So if I'm substituting this in the next step, well, the exponential turns into an e to the minus I k n hat I xi minus omega over k t, just factoring out the k. Now the next thing you may remember from one of your previous physics classes is that omega over k for a wave is its phase velocity. So if we substitute this now into our top level equation here, what we get is we get a time derivative that gives us a, let me be consistent with my notes and remove this minus sign here in front. It doesn't really signify anything, but then at least what I'm having on the blackboard is the same as what you have in the notes. Is the time derivative of the exponential. We have a minus IV UA, U alpha. And we get from the second term the spatial derivatives here. That gives me a plus IK B K alpha beta. And now the partial K derivative acting on the Xi pulls down the Ni, Nk times U beta. I'm somewhat double using K. This K here is a summation index. This K over here is the wave number. And I am missing a K over here as well, because we have K times V as the thing over here. And all of this is still SA, as alpha. Let's divide by IK, and then we have the equation V U alpha plus beta K alpha beta Nk U beta equals 1 over ik as alpha. Next step is to take the short wavelength limit. That means k goes to infinity. The only k left is on the right-hand side, and so the 1 over k is going to kill the S alpha. And what is left are only these two terms here, where I have forgotten the minus sign. And so what we then have is that moving the v u alpha to the right-hand side, we have on the left-hand side a matrix P alpha beta of n multiplying U beta. And this P alpha beta is called the symbol of the equation. It is BK alpha beta NK. And so what we now have here is precisely an eigenvalue equation like the one Geoffrey has already mentioned yesterday. So the short wavelength traveling modes of the hyperbolic system are determined by an eigenvalue equation. The eigenvalues are the velocities. And the eigenvectors are the distribution of how each of our variables is being excited in this traveling wave. And so at this point, we can make a few statements about classification of hyperbolic equations. Yes?
Sorry, me, I missed it. Where is that exponential term? Last second line. No, below that one. When you are substituting in the first relation, there should be an exponential term, right?
Here.
Yeah.
Yes. You're right. Here's an exponential. There's an exponential term everywhere.
Yeah.
And that means if I don't put them on the left-hand side, I need to put them with an e to the minus ik on the right-hand side. You're absolutely right. It still goes here, thank you. But it then disappears because this whole thing is going to 0.
Sorry.
It then disappears with the entire right-hand side here because of the 1 over k. Thank you. Thank you for correcting this. Geoffrey?
So this eigenvalue equation holds only for short wavelength. But we won't be able to resolve.
That's, as it turns out, that's what matters. I don't really have a good explanation why. Okay, so we have an eigenvalue problem. And now we can think about unless there's more questions. Now we can think about how many solutions we're going to have here. So let's go through a few different cases. So the nicest case is if our symbol is symmetric, or symmetrizable, then we have n linearly independent eigenvectors. I'm going to call them R beta, and I'm going to label them through with an alpha hat. So alpha hat is going from 1 to however many variables I have. So for symmetric matrices, the eigenvalue problem always has a full set of eigenvectors, and the eigenvalues are real. So the eigenvalues I'm going to call V alpha hat. There's one V that goes with one eigenvector, and those are real. And this is called symmetric hyperbolic. As it happens, our scalar wave is in this category. The importance of this, having a full set of eigenvalues and eigenvectors, is that we can decompose our solution completely into oscillatory traveling modes. So what else can we have? Yes? Scalar wave. Our scalar wave equation is in this category. As an example, we had the B matrices yesterday on the blackboard, and somebody remarked, hey, they're actually symmetric. And so this actually is precisely the definition of symmetric hyperbolic, which is the nicest set of hyperbolic equations to have. Yes? Yes, I wasn't actually quite sure about that, because when I wrote them down, they were symmetric. I think Geoffrey broke the symmetric hyperbolicity with one of these constraint damping terms. We can figure it out in the break, Geoffrey and I. The next thing you can have is, the nice thing about having the matrix symmetric itself is there is a simple algebra theorem, linear algebra theorem, that just implies this without you actually having to compute anything. Otherwise, what can happen is that Pn is still nice and is still having a full set of eigenvectors. And real velocities. And in that case, one is basically in the same situation as down here, as above. Still good. And this is called strongly hyperbolic. And then there's a third case. P has all real eigenvalues, comma, but no complete set. Set of eigenvectors. This still has a name, although the name isn't really that useful. It's called weakly hyperbolic. And the importance for this classification is the following theorem. Strong, symmetric and strongly hyperbolic systems are well posed. Weakly hyperbolic ones are not. But not weakly hyperbolic ones. So we need to be in one of the first two categories here. This is good. And not in the third one. The reason that this is significant for numerical relativity is that the first set of evolution equations that was derived at the ADM equations in the 70s, I'm pretty sure Thomas talked about them last week. Those were, after a lot of trial and error and with numerical simulations, found to only be weakly hyperbolic. And somewhere around that time it was realized, well, the numerics doesn't work, these things are weakly hyperbolic, so actually our inability to solve the equations on computers is related to the mathematical properties of the equations. And the current evolution systems, like the BSSM equations that Thomas talked about last week, or the generalized harmonic equations that Geoffrey talked about this week, they are all in the good categories, usually symmetric hyperbolic, but at least symmetrizable hyperbolic, at least strongly hyperbolic. Okay, I haven't told you yet what well-posed means. Well-posed is a combination of three things. Number one, a solution exists. It's always a good thing to have. Number two, the solution is unique. If you had a situation where one set of equations actually gave you two solutions that are both satisfying the equations, well then, A, we wouldn't really know what to do with it, even on the analytical level, but even less the computer. So these two things are totally obvious, I hope. And the last quantity is somewhat more obscure. The solutions depend continuously on the initial data. So if you change your initial conditions by epsilon, a very small epsilon, then the subsequent evolution should also only be changing by a small amount. In letters, this boils down to something like this. The norm of u at different times has to be bounded by an exponential with some constant in front of the time times the norm of u at time equals 0. And this looks obscure, so let me give you a counterexample, just to get you a sense of how things can actually go wrong. Let me write down a very simple set of equations. It only has two variables. The first one is u1. Its time derivative is plus the spatial derivative of u2 is 0. And the time derivative of u2 is 0 just by itself. If you work out the B matrix, you only have one derivative term in here. So the 1B matrix, because this is 1 plus 1 dimension, only one space dimension, has entries 0, 1, 0, 1, 0, 0. And it has two eigenvalues, namely two of them, they are both 0, but it only has one eigenvector. I guess I'm just a little bit too short here in the corner. So let me switch over and keep on writing here on the left-hand side. And what I now want to do is I want to use a very special initial condition here. Namely, I want to take u1 of x comma 0 to be 0. And I want to take u2 of x comma 0 to be epsilon times e to the ikx. That means the norm of our initial conditions are of order epsilon, and epsilon is some small number. It doesn't actually really matter what norm you're putting here. Depending how big your domain is, you might use somewhat different ones, but that's mathematical fine print. So we have initial conditions with very small norm, but, and this is where the problem comes in, if I'm looking at the time derivative of u1, well, this is minus u2 prime, and so this is going to be minus epsilon k I e to the ikx. And the problem here is that the k is coming down. And so that means that u at some later time is going to have the size epsilon times k. And this can be an arbitrarily fast blow up for large k. So what happens if you try to do this on a computer is the following. Once you put down some numerical grid with some resolution n, this is telling you the maximum k you can resolve on your grid. And because higher frequency modes, the higher the frequency, the bigger they blow up, any power you have in this highest mode you can still resolve, even if it's just random noise coming from 10 to the minus 16 round of error, is going to grow quickly. And if you now increase your numerical resolution, as I've always telling you, you need to increase resolution and make sure you get the same answer. What then happens, your grid now suddenly can support modes with higher k because now you have higher resolution. So you find something that's growing more quickly. And so as you increase resolution, you don't get the pictures I have on my demos, that you get ever more precisely a nice solution. But what you would be getting is that you get a solution that blows up ever more quickly in time, the higher resolution you have. And all of this due to the fact that there aren't a full set of eigenvectors. So this has been the first part of a somewhat more theoretical part. So let me pause for a minute here and see whether there are any questions.
Another question. So since strongly hyperbolic systems also have a full set of eigenvectors.
Yeah.
So does it mean that by change of variables, strongly hyperbolic system can also be converted to symmetric?
Yes. So if you change variables, you can go between these categories and even outside the categories. Because, for instance, if you define a new variable that is a combination of other variables, you are redistributing the numbers in your B matrix. And the other thing that Geoffrey was talking about is this trick of constraint addition, that you're adding constraints to your equations. These constraints had derivatives in them, so they will lead to extra entries or modified entries in the B matrices again, which again could change all this business over there. And both the ADM equations that live over here in this bad part, as well as BSSN and GH that live in the good parts, they are both representations of one and the same Einstein equations. So if you have a set of PTEs like Einstein's equations and you turn them into first order form, depending how you do this, you can end up with something bad or something good. It's weird. So there's one more step I need to do here. And for that, I think I want to keep that stuff over here. So can I erase the example again? And that is the fact that we did have a traveling mode here, that u of x and t was u0 e to the minus I kx and so forth. But our traveling mode was still spread over all our evolved variables. So it has some power in g, it has some power in pi, it has some power in phi. We would like to isolate this into one only variable. And it turns out to isolate traveling modes, we need left eigenvectors. And so just to remind you what left eigenvectors are, I'm calling them capital L, alpha, P alpha beta of n. So the P is our B matrices dotted into the n direction, still the same as before, equals V left. It turns out that the left and the right eigenvectors share the same eigenvalues. So these eigenvalues, I'm still labeling them by alpha. Those are the same as for the right eigenvectors. And I also need to label through my left eigenvectors because I'm going to have n of them by an index alpha hat. And so the alpha hat is going to run again from 1 to the number of equations, just counting through the left eigenvectors. And so the question you might have is, why do you now suddenly show up the left eigenvectors? And to see this, let's go back to our situation over here, where we have a direction n in which our waves are traveling. And we have, say, one wave with a certain wavelength λ1 and a certain velocity v. And we have a different wave that's also going, well, it's going at a different speed. Say, have this v2 and this v1, and it may have a different wavelength. Actually, the wavelengths aren't really important because we have gotten rid of them by going to a short wavelength limit. We have this situation, and so we assume that u of x of t is a superposition of waves with same n. So we have all our eigenvectors, they give us 5 different waves with 5 different velocities, and we now have a superposition of this gunk. And because we have plane waves orthogonal to n, what this means is that derivatives orthogonal to n vanish. And what this now means is that the derivatives of u alpha turn into only derivatives in the n direction. So it's n hat times the derivative in the n direction of u alpha. If I now substitute this thing into my original evolution equation, well, the evolution equation looks like u dot alpha plus b alpha beta k. Now this thing comes in here. So I have an nk dn of u alpha no hat just yet, equals whatever right-hand side we have. We can now take this equation and multiply it by the left eigenvectors. So I'm multiplying by the alpha hat left eigenvector. That goes here, that goes there. It also goes on the right-hand side, but the right-hand side doesn't matter, so who cares about it being in the right-hand side? And now we have here precisely the reason why we have the left eigenvectors coming in. This thing here is v alpha hat times L itself. And by the way, I'm using these parentheses here to indicate no sum over alpha hat in this particular equations. And so what we now have is, okay, so we have this equation, and now we are defining our characteristic fields. Namely, u alpha hat is equal to L alpha hat alpha u alpha. So if we do this, the first term turns into a u alpha hat dot, the time derivative of the characteristic field. The second term, the velocity is here. The second term turns into a partial derivative of the characteristic field. And this is whatever right-hand side we have. So this equation pretty much looks like all the other equations that I have on the blackboard. I'm always seeming to write very similar looking equations. But one important difference here now is that on the left-hand side, we don't have any coupling anymore between different alpha hats. In this equation here, if you plug in alpha hat equals 1, you only have the first characteristic field and the first characteristic field's derivative, and no other characteristic field showing up, and similar for all the other ones. So in the characteristic fields, the principal parts decouple, and each characteristic field moves independently of all the other ones, well, with its own velocity v alpha. So let me put this on the blackboard. The principal parts have decoupled. And each u alpha travels individually with its own speed, with its own speed v alpha. And if v alpha is positive, the travel is into the direction of n hat. And well, if the velocity is less than 0, then the mode still travels, but in the direction opposite to n hat. Well, that's just minus n hat, of course. Okay, so that's it. That's why these modes show up. And if we now have a boundary, we need those modes, and we need only those modes that are coming into our domain to apply boundary conditions to. Haha, excellent question. I was trying to smuggle this past you. Over here, to get from here to here, I had to move the L matrices under the derivatives. For the scalar wave system we are working on today, this is trivial because the L matrices are constants, so we can just move them in. But in general, the L matrices will depend on space, and they can also depend on the instantaneous state of your system. So there can be the variables themselves in them as well. And in that case, I think what a remark Geoffrey made yesterday applied, that in a certain limit, it's still okay to move things in. So we now want to solve our wave equation. Xg equals 0. We have our boundary sitting somewhere of our domain. And so we're going to choose n to be the outward pointing normal to our boundary. And now if a mode travels right, this is a mode with, say, v alpha bigger than 0. It wants to leave the domain anyway. So for that mode, we have no boundary condition. And if a mode comes in, I shouldn't be using green, somebody told me. If a mode comes in, this is one where we have v alpha less than 0. This one needs a boundary condition. So we end up applying boundary conditions exactly and precisely to the modes that have negative characteristic velocities.
The eigenmodes corresponding to different eigenvalues have different convergence rates.
Would the eigenmodes of different eigenvalues have different convergence rates? I don't think so. I think this will depend on what the physics of your solution actually contains. If you have a physical situation where whatever is leaving your domain has very long wavelength, because that's what your physics is, but you now choose, for whatever weird reason, to feed in something with very high frequencies, then yes, you would need higher resolution to resolve this high frequencies thing you have fed in. But this is not because of anything in the hyperbolic system. It's because of the physics and the boundary condition you choose to apply in your particular case. It can happen, but it need not happen.
I was wondering if this is related in any way to anti-grid methods.
No, not at all. Multigrid is a scheme for solving elliptic equations and not for hyperbolic equations.
Boundary conditions for modes which have zero characteristics.
For zero characteristic speeds, you don't really need boundary conditions. I think it's okay to apply them, but we generally do not, simply because our philosophy is to make the least possible amount of changes at the boundary, both because of the work we're doing in coding it and because it works. Yes. So if you have a zero speed mode, you basically have an equation like u dot alpha equals whatever is the right-hand side. And so as long as whatever is the right-hand side is already doing what you want and you don't get any artificial blowups, then you are fine. Okay, so let me briefly outline how this now actually works in practice. So the overall procedure is the following. At a boundary point, say we have the highest point x n minus 1, the rightmost boundary. With a boundary normal ni, say nix equals +1 if we are in one dimension at the outer boundary, at the upper edge. We compute the left eigenvectors. For the scalar wave, then of your derivative matrices n hat k, then you compute the characteristic fields, or with the eigenvectors come the characteristic fields. U alpha hat equals L alpha hat alpha U alpha. Let me put this down for the scalar wave in 1 plus 1, 1D. The eigenvectors are, let's call them 1, is 1, 0, 0. I think, Geoff, we had this already. 2 is 0, 1, 1. And 3 is 0, 1, minus 1. The speeds are v1 equals 0, v2 equals v3 equals. And now I'm in the situation where I'm doing things I shouldn't be doing because I don't have this in my notes. And I don't remember which one of the two is the +1 and which one is the -1. Geoffrey, do you happen to remember? I'm in 1 plus 1D. I only have 1 phi. And so if you now go, let's worry about these. Once I put something on the screen, then I can tell you what the signs here are. And along with these now goes the characteristic fields. So U alpha hat from this one here is 1 times g, 0 times pi, 0 times phi. So this is just g. U2 would be pi plus or minus phi, once I figure out what the sign is. And U3 would be pi minus or plus phi. Once I figure out what the sign is, I have it in my notebook. So you have these three things. And all these characteristic fields are some linear combination of the actually evolved fields. Because, well, this transformation here is linear. It's a matrix multiplication. Okay, so we have our characteristic fields. The next step is to evaluate the usual volume right-hand sides, volume d by dt. So we get the usual d by dt, dtg equals dt pi equals dt phi equals, by evaluating the scalar wave equations. Transform these, and I'm calling these dt u alpha. We now transform these to characteristic fields. So we compute dt u alpha hat by the L matrices hitting the dt u alpha. So what this means is basically means that you put periods on top of everything here. And now comes the state where we actually evaluate and impose the boundary conditions. Namely, for those fields where V alpha is negative, we replace the volume time derivative by whatever boundary condition we want to impose. This is an incoming mode. It needs simply to be told what it is. So we are replacing it by something we have the freedom to choose ourselves. So this is our user choice, or it's the physics dictated by the physics of the problem. For instance, if you don't want to have anything come back into your domain, then you can set this to 0. If you have something else, like you're shooting for some moving scalar wave profile, then you can use this to inject the instantaneous value of your profile, and that way feed it into the interior of your volume. And so this is the important step. Then afterwards, lastly, you transform back to the time derivatives of the actual fields you're evolving. And this is the inverse of this transformation over here. So basically, you're solving these three equations for g dot, pi dot, and phi dot. And that is then what ends up being the important quantity that you're feeding into the time stepper. So we are using this, use these dt u alpha at the boundary point. So this is somewhat abstract right now, for the two reasons that number one, I'm showing it now on the screen with the example. And number two, doing this for the scalar wave is your tutorial for this afternoon. So I don't really want to take all your work away. So let me show you nevertheless how this ends up looking for the scalar wave case. So this is basically the same code we had yesterday. I have a few different pulse shapes floating around here. Yesterday we used the periodic ones. For today I also have non-periodic ones, which are, wherever it is, here. They're Gaussians. So e to the x squared. And then I have here my Chebyshev scalar wave equation. For Chebyshev, I need a lot more pieces of information to make things work. And I'm storing all these extra pieces of information inside info. I'll show you in a minute how they get there. And so the right-hand side of the Chebyshev scalar wave equations looks as follows. I'm getting pi and phi out of the variables that are being passed in, U1 and U2. I could also get back G, but it turns out G doesn't show up in the equations, and Visual Studio Code then grays out the G here because it's not being used. And I found this a little bit unpleasant seeing the gray, uncomfortable seeing the gray G here, so I removed it. Here we evaluate the time derivatives in the volume. These are the usual scalar wave equations. You've seen those as well in the Fourier case yesterday. And in the Fourier case, we would put them into du dt, and we would be done. Here, however, comes now the extra step, the extra procedure that I have outlined here on the blackboard. First, I equals 0, the lowest grid point. I am computing the time derivatives of the characteristic fields. Those are these yellow equations over here. You had 0, you had 1, you had 2. And it turns out on the left-hand side, it is the first one of these that has the negative speeds. And in this particular case, I'm feeding in information from a function I'm calling left boundary conditions. And it turned out if you want the function left boundary conditions to be the actual shape that is traveling through your domain, then this one here has to have 2 time derivatives. The reason is actually not that complicated to understand. We have one of these characteristic fields is pi plus phi, and this turns out to be minus g plus gradient of g, minus g dot plus gradient of g. And if you now want to have g being some, say, right moving function of x minus t, then this thing is going to be a r prime plus r prime. But the boundary conditions require to specify the time derivative. So if I'm now putting one more derivative here on top, this turns into one more spatial derivative of the shape of the pulse moving around. So that's why we need the second time derivatives. So you basically simply replace the relevant time derivative of u hat by whatever your choice is. And then you invert the yellow equations on the right and put that back into the corresponding grid point of the original evolution equations for G, pi, and phi. You do this once at the lower boundary, you do it once at the upper boundary, and here the upper boundary is the one that's going to tell me what is what. So the one with the negative speed is pi minus phi. Pi minus phi has the negative speed. Then this one here has the positive speed. This one here is plus, and this one here is minus. Okay, cool. And this piece of code is utterly identical to the one we've just went through, except that at the opposite boundary, whatever mode is moving left on the lower boundary into the domain, that's the one that's going out at the other side. And whatever is moving left into the domain of the upper end is going out at the lower side. So it's the opposite mode that needs a boundary condition here. So at the upper boundary, it's the second fundamental field. At the lower boundary, it was the first fundamental field that needed a boundary. But otherwise, all of this is the same. Then again, converting this particular grid point back to the physical variables, and ultimately putting everything into the variable dutt that is then being passed back to the time stepper. So this is a little bit complicated. I hope it becomes clearer when you actually write down the concrete equations for scalar waves this afternoon and work through this yourself. So if I'm actually running all of this, and let me run this first with zero boundary conditions. Okay, I need to re-evaluate everything. Let me just do this. It doesn't take very long. Wait a second, left PC, what am I doing here? That's the Chebyshev scalar field. I'm somewhat confused right now, so let's see what this actually does. Oh, this is already doing the full thing. Don't I have it simpler? Oh yes, I have it simpler over here. Good. Okay, I'm confused. Because I now have, curiously enough, something that runs. Ah, cool, here we go. So here's now how the solution looks like if I'm using zero for these boundary conditions on both sides. I'm starting with a pulse right in the middle of the domain. As in the Fourier case, it's going to travel right, time equal 1, time equal 2, time equal 3. And it just disappears off at 2 pi. Time equal 4, you see a tiny little edge of this Gaussian, but afterwards there's nothing left and we just have 0. So the pulse is happily leaving the domain. And in this next example, I'm actually confused how these examples work. I shouldn't have to say this, but I do. So let me see. I have a function called setup Chebyshev scalar wave. Well, It takes a resolution, perfect. It takes a starting time, perfect. And it takes a left boundary condition and a right boundary conditions, which are some of my function objects from further up. But I don't see in here where it is choosing the initial conditions. So let's go into setup Chebyshev scalar wave and let me unconfuse myself here. Here's the setup Chebyshev scalar wave. Is the font size okay? And that gives me an opportunity for explaining this info thing one more time, or highlighting that it is now more complicated. So this info thing now is going to keep the same dx min and x, the grid information as before, but I'm also storing all the Chebyshev matrices inside of it. And I'm also throwing in the left and the right boundary conditions. So when I make this info object over here, it will remember everything it's going to need for the actual evolution equations. And if I'm going back a little bit to the evolution equations, you're seeing that I have here sitting code like info.d1 multiplying phi. So that's how the differentiation matrices get around. I'm sticking it into info. That way they can get through the time steppers without me having to change the arguments that go into the time steppers. So that keeps the time steppers nicely separated from the specific evolution system. Okay, so info. But now I wanted actually to look up where the initial data is coming from. It is taking G as the sum of the right moving and left moving things that I have passed in. So it is setting up the volume already as R plus L. And the fact that made me so confused down here is that everything started with 0. But here everything starts with 0 because the left moving pulse is here to the right of the domain at time minus 5.7. It's then happily moving into the domain and out on the right-hand side. And the right moving pulse is to the left of the domain, but also still outside. That's why in the first panel nothing is showing up. Then you see the right moving pulse slowly entering at 4.7 and 3.7, minus 4.7, minus 3.7. And I have set up things such that the left moving pulse comes first. It happily goes left and left and left and more left. You see the time in each panel. And now at about time of 0.3 or so, you begin seeing the right moving pulse entering here. Here, they're on top of each other, leading to very big magnitudes. Now the right moving pulse is almost gone, and the left moving pulse is happily going left. And a little bit further, I hope the left moving pulse is going to disappear on the left-hand side. So all of this actually works out at the end of the day, as surreal as all this math formalism might sound. Okay, that's what I had about evolutions of wave equations with spectral methods and how to do boundary conditions. I have about 20 minutes left, and so I wanted to come back to a topic that came up in the first hour, in the first lecture on Monday: what type of basis functions to choose.
Before you raise, so there's a technical error.
I'm sure there is where?
So this R double prime plus R double prime, it should be minus R.
They should both be minuses.
Because they are functions of x minus t. When you take another derivative.
Okay, this is also fun. Let's go back and let's remove these time derivatives for a second. And let's figure out whether we are agreeing on what's written down here so far. So pi is minus g dot, g prime. The g dot gives me a minus sign. So I think this one is correct. And so this one is correct. And if I'm now putting the dots back,
Okay, so both of them.
So both of them should have a minus sign. So this should be minus r double prime, 2 r double primes. Thank you. And so what you're seeing here, by the way, is that U1 is seeing the R field. And if I'm also evaluating the same thing for U2, that would be pi minus phi. And so that would be minus g dot minus g prime. And that would be plus r prime minus r prime. And that would be 0. So as it happens, the U1, the right moving mode, is constructed in such a way that it is only susceptible to R, the right moving part of the solution. Whereas the left moving mode, U2, if you evaluate it for a right moving solution, you get 0 because, well, the right moving solution doesn't have a left moving component. And so if this were a combination, right moving plus left moving, the left moving would be cancelled out here, out of the right moving mode. And the left moving mode would only have the L left down here. So this is a nice way, another nice way of visualizing this, that the characteristic modes are actually precisely selecting the left moving and right moving portions of your overall solution. So what I wanted to do briefly is go back to the question of why don't you use Taylor series but Fourier and Chebyshev polynomials? And one thing I always find quite astonishing about this is actually how dramatic the difference is between, say, doing a Chebyshev expansion and a plain old Taylor series. And so let's briefly look and highlight the convergence domains. So the question is, we have some function u of, actually it's now a u of z, and z element complex numbers. And we've always looked at u of x so far in everything we've done, but for the convergence domains, you actually need the complex numbers. The question is, where in C does the expansion converge? The question will become a little bit clearer once I'm back at the Taylor series. And it turns out the convergence both in C but also on R Convergence depends on the singularities of U of Z. So for instance, if I'm thinking about the function U of x equals 1 over 1 plus x squared, well, if you go into the complex plane, you have singularities at Z equals plus minus I, because, well, for I, the x squared is minus 1, you get 1 over 0. That's the function blows up. And so a Taylor series converges in a circle largest circle in C without singularities. So let me put up the plot here on the right-hand side for this. So we have the real part, x. We have the imaginary part. We have our singularities at plus I and at minus I. And that means the Taylor series is only going to converge in the circle of radius 1. So if you Taylor expand 1 over 1 plus x squared, as nice as this function looks like, if you're trying to evaluate the Taylor series at 1.2, it will fail. It fails over here to evaluate because of this pole on the imaginary axis. For Fourier, so for the Taylor series, the important term is circle. For Fourier, converges in widest strip imaginary part Z less than or equal to a constant, the widest strip without singularities. So in this particular case, the Fourier would converge in a strip that goes between plus minus 1, and that goes all the way up to the pi and even beyond pi, because the Fourier series is going to be periodic. So even if you're just thinking about the real axis, the Fourier series will converge everywhere, whereas the Taylor series will not. Of course, with this example here, the Fourier series will converge remarkably slowly, because if you consider this as a periodic function, and then you put the next copy next to it, you will have a small discontinuity here, where the first derivatives don't line up. So you won't get exponential convergence for this particular choice of function. Okay, but Fourier tends to be better than Chebyshev, than Taylor. And here the operational terms are widest strip. Chebyshev, this is where things get curious. I'm actually quite amused by this result. A Chebyshev series converges in largest ellipse without singularities inside, But for the ellipse, we now also need to specify its shape and so forth. And here, the trick is that the foci, the two focal points of the ellipse, at the end of the Chebyshev interval. So if I'm going back to my plot over here, if for whatever strange reason, I should be deciding to do an expansion, say, between minus pi and pi, I don't know why you would choose minus pi and pi, except that I want to have it consistent with the Fourier series in this particular case. Then these are the focal points of your ellipses, and the ellipse needs to go through the closest singularity. So Chebyshev is going to converge in a regime that looks something like this here. And the important points here now to note, since we are, so these are the complex plane results, but since we're only interested in real numbers, what this boils down to is that the Fourier series, the Taylor series, only works on typically on a reasonably short part of the real axis. Chebyshev and Fourier series can go all the way between plus minus pi for this particular example, if I happen to choose plus minus pi. Let me show this with a little demo. The little demo, I believe, shows a different function, but that's perfectly fine. So the function I'm using here is a cool thing that Boyd has in its book. It's basically the same as this Lorentzian, but the example that I'm using now in the slides is Boyd equation 224. He calls it the function lambda of x comma p, and this can be written in three different forms, curiously enough. 1 plus p squared minus 2 pi cosine x. And you can write this for once actually as a sum of many Lorentzians. So you have the sum of 2a divided by a squared plus x squared minus 2 pi m, and m goes from minus infinity to plus infinity. So for what this is a sum of Lorentzians that are offset from each other by 2 pi. And so by adding all these Lorentzians together, you're guaranteed to get something which is periodic. And so you're actually getting a very nice Fourier expansion for this thing. But if you're looking at this whole thing near zero, it looks pretty much exactly like this case here, where you have the m equals 0, 1 plus x squared term, limiting the Taylor expansion around 0. This function can also be written, and I'm continues to be amazed by this example, as 1 plus sum over n, n equals 1 to infinity, 2p to the n cosine nx. So this is actually directly a Fourier expansion here, where each mode has the amplitude to the 2 to the p to the n. Okay, anyway, sorry for spending so much time explaining what this funny function is. Let's try and plot it. or not, whatever this warning is. I wanted to take this one out. So here's the function where I now have put in a 2 pi for no good reason, but it doesn't really matter. I think I put the 2 pi in because Boyd has the version with the 2 pi. It basically looks like a Lorentzian. And if we put the spectral coefficients next to it, then the spectral coefficients nicely go exponentially down as they should. And so with a few Fourier cosine modes, you get tremendous precision. Now let's do a Taylor series of this thing. I've only messed up in the first example here. I shouldn't have put the 2 pi's up there, but doesn't matter. So the thing I'm Taylor expanding doesn't have the 2 pi inside of it. I'm doing this with SymPy, doesn't really matter. So let's just do it. And this takes a few seconds. And first focus on the 2 left points here. The left top one plots the individual Taylor series terms up to x to the 20th. And so in the middle, everything is nicely small. And even here at minus 0.9, you see that the terms become smaller 1 by 1 by 1. So here the Taylor series still converges quite nicely. Down here is the actual sum of the Taylor series. And so if you go from the 0th term up to the 4th, 8th, 12th, 16, 20, it really looks like it's converging to the Lorentzian. The right panels plot the very same thing, except that I have increased the x range a little bit. And now if I'm going to somewhat more than x equals minus 1, you see now each individual term becomes larger than the one before. And the series as well becomes larger with each term that you're adding to it. So over here, the Taylor series is going to diverge. And the dashed line here is actually the location of the closest pole on the imaginary axis, indicating and demonstrating really nicely that the Taylor series is going to converge up to the first pole, even if the pole is complex and not visible. And as you see on the left-hand side, even away from the pole, the convergence rate of the Taylor series already gets quite a bit worse the closer you come to the pole. Okay, so this is the Taylor series. And I hope the next one is the same plot for the Fourier series. Yes, here's the same thing for the Fourier series, just plotting in a different way. Here, the Chebyshev series, I apologize. So we're going over the full interval from minus pi to pi. Second order Chebyshev is just a parabola. And then as you go up in order, these things actually nicely converge to the true shape in the entire interval, and not only in plus minus 1 as the Taylor series does. And the Chebyshev series is also nicely exponentially convergent. So if I had summed up 80 terms, I would have been at 10 to the minus 12 in accuracy. And at 20 terms, I will have about 3 significant digits. Okay, just one more example why Chebyshev series or other spectral expansions, also the Legendre polynomials of Geoffrey, are really cool and are really way more powerful than a plain old Taylor series. Okay, I'm at the end of the lecture now. Thank you all very much for your attention throughout this week. It was a big pleasure teaching here. I had a lot of fun. And I also hope that you took something useful away from these classes. Thank you very much and good luck for your future endeavors.
Okay, so if there are no more questions, I just wanted to say that this is the end of the lecture part of Harald's course, and I personally want to thank him for sparing his time, for being here and preparing for and delivering this course. So let's thank him warmly again.